All right, today we are jumping headfirst into a debate that's been around for, well, a very long time in the world of mathematics. When does genius really strike? Is it a flash of brilliance when you're young, or is it something that comes only after a lifetime of hard-earned experience? Let's dig in and investigate. And our starting point, our central clue, comes from this really famous, and you gotta admit, pretty provocative, claim by the British mathematician G.H. Hardy. He flat out said that math is a young man's game. Wow. That one sentence right there, it sets the stage for everything we're going to look at. The big question is, was he right? So to really get to the bottom of this, we're going to treat this whole thing like a case file. First, we'll put Hardy's claim under the microscope. Then we'll look at the evidence for both sides, the young guns and the seasoned veterans. We're also going to introduce this really cool metaphor, the conceptual mountain, before we dive into over 500 years of actual historical data. And at the end, we'll deliver a final verdict, especially for all you educators out there. Let's get started. Okay, first things first, we have to really interrogate this idea. What was Hardy even getting at when he said mathematics is a young man's game? And, does that claim actually hold up when you look at it closely? Now, before we go any further, we have to talk about the wording here. Young man's game? I mean, that phrase totally ignores the incredible contributions of female mathematicians, and we absolutely need to acknowledge that. But for this investigation, we're going to zoom in on just one part of his claim, the young part. That's our focus. All right, let's bring in Exhibit A, the case for youthful genius. What is it exactly about a young mind that makes it so powerful, especially in a world of pure abstract thought like math? The argument for youth really boils down to these three things. First, just immense creativity. Young thinkers often aren't bogged down by the way things have always been done. And that leads right to the second point. They can shine a completely new light on an old problem, which of course results in the third and maybe most important point, thinking in ways nobody has ever thought before, just coming at a problem from a completely different, maybe even radical angle. But hold on, that is only one side of the coin. It's time for Exhibit B, the case for deep experience. This argument says, hey, all that creativity is great, but it's pretty much useless if you don't have a solid foundation to build on. And this right here is just simple, powerful logic. You can't solve a puzzle if you don't even understand the pieces. I mean, think about it. To even start working on some big, famous conjecture, you need a seriously deep grasp of all the concepts involved. And that kind of understanding, it only comes from a ton of knowledge and experience. And this slide just lays it all out, this central tension in all of this. On one side, you've got youthful genius. That's your immense creativity, fresh perspectives, and a real willingness to break the rules. And on the other side, you've got deep experience. That's vast knowledge, the skills to spot hidden patterns, and a complete mastery of all the mathematical tools. So the real question becomes, which one matters more when you're trying to make a huge breakthrough? To really get our heads around this tension, we need a better way to picture the problem. So let's introduce a metaphor that I think perfectly captures what it takes to make a real discovery in math. We're going to call it climbing the conceptual mountain. So what exactly is this conceptual mountain? Well, just imagine the entire body of mathematical knowledge as this huge, sprawling mountain. It's got layers and layers of ideas built on top of each other. And if you want to make a new discovery, if you want to prove something nobody has ever proven before, you have to climb that mountain, all the way to the top, to the very edge of what we know. And the climb up this mountain happens in stages. You start at the very base with the fundamentals, axioms and logic. Then you move up into the foothills, mastering the big areas like calculus and algebra. From there, the climb gets way steeper as you get into really specialized, complex topics. And only after all that work do you finally reach the peak. That's the frontier, the edge of everything we know. That's where the unproven conjectures are, just waiting for someone to solve them. Okay, so we've got the arguments for both sides, and we've got our metaphor of the mountain. But how do we actually put Hardy's claim to the test? Well, now we shift from theory to evidence, with a kind of forensic analysis of history itself. And this is the million-dollar question for our investigation, isn't it? How on earth can we check a claim like this against centuries of history? How do we take this debate and turn it into something that data can actually help us answer? Well, the answer is data. For this analysis, we're using a really cool comprehensive source, the Timeline of Mathematics page on Wikipedia.
It's basically a massive, publicly built log of all the major mathematical achievements through time. And look at the sheer scope of this data. It's pretty incredible. The analysis covers major mathematical events over a huge period, more than 500 years, stretching all the way from 1501 to 2015. And we're talking about a lot of data points here. Roughly 250 different significant mathematical events were analyzed. So this whole investigation has a really solid quantitative backbone. And when you actually crunch the numbers on these 250 events, something really surprising starts to emerge, a pattern that flies directly in the face of what GH already claimed. So to get that pattern, we first need to know what we're looking for. What counts as a significant event? Well, it could be the first ever proof of a theorem, the publication of a really important paper, or even the birth of a brand new mathematical idea. Now, here's the kicker. By tracking the age of the mathematician for every single one of these breakthroughs, the data shows that the average age for a major discovery has actually been going up steadily over the last few centuries. It seems our conceptual mountain is getting taller. So, after looking at the arguments, the metaphor, and now the historical data, it is time for the final verdict. And more importantly, what does this surprising trend mean for us, for the people in the classroom teaching the next generation of mathematicians? So, was Hardy right? The data gives us a pretty clear answer. Nope. In fact, it points in the exact opposite direction. But, the real takeaway here isn't just about proving an old quote wrong. It's about understanding why. Why is the age of discovery getting older? And it all comes back to that dance between creativity and knowledge on a mountain that just keeps growing. Okay, let's just boil this all down. What have we really learned? First, that genius isn't just one thing. It takes that creative spark we so often see in young people for sure, but that spark can't really light a fire without the tools and the deep understanding that only come with experience. You need both to get to the top of that conceptual mountain. And what the data is telling us is that as math knowledge grows, the climb to the frontier just takes longer. It takes more time to build that foundation before your creativity can really make a difference. And this leaves us, as educators, with a really critical question. In a world where that conceptual mountain is taller than it has ever been, how do we get our students ready for a longer and, frankly, a steeper climb? How can we design our classrooms and our lessons to nurture that amazing, creative, rule-breaking spark, while at the same time building the discipline and the patience they need for a journey that might take years? That right there is the real challenge that this whole investigation brings to light for us today.